Thanks for the introduction. Yeah, so I would like to give some insight into homogeneity, isotropy of a tape-like. So it's like a pop-up reverberation chamber. As said, some credit to my co-authors, Sebastian Wesselis, from, as it's written here, Statex, or it's better known as Shieldix. They also have a booth outside, and he provided us with the chamber. So, some motivation, you should all know about reverberation chambers, but there have been some developments in the last decade. So we also have fast field probes now, for example, from Lumio. They also have a booth outside, and these fast field probes allow for fast electric field measurements. And if you can measure fast, you can also steer fast. So we had a paper last year that's on in the Europe conference. You can see our large chamber with the large steerer, then we have a smaller steerer that we can rotate very quickly. And we also try if we have a chamber with solid walls, what would happen if we put like a flexible steerer inside there, and with much less motor power, you can also do very rapid mechanical movements there. And so fast probing, fast steering allows for fast analysis. If you have powerful computers, you can do all the statistics in real time. And this also allows for direct field strength control. So there's some ISO standard that's now used in the automotive industry that allows a direct field strength control for immunity testing, which is very powerful. So fast probing, fast steering gives low statistical uncertainty, very quick and reliable measurements in reverberation chambers. And another thing is that there are these pop-up chambers that you can use for flexible operation, and not like this. I mean, this tent you can also just put down. And this is the chamber that we use. So this is how it looks like when it's not set up, and then you need about like 1 hour, maybe if you are very experienced, maybe like half an hour to set it up. And so I would like to show some results that we did with, or that we got from this chamber. So after this introduction, I will show you some more insights into our measurement setup and the procedure. And then we will take a look at spatial standard deviations of the field, so at the homogeneity, and then we also analyze the isotropy or anisotropy coefficients, and from them also cumulative distribution function, and at the end, of course, I will draw some conclusions. Okay, so this is, if you like take this hour, set this chamber up, it looks like this. As you can see on the outside, with some aluminum frame that is just screwed together. Then we have this tent, which is made out of metallized textile. It's just fixed with rubber straps, so it's fairly tight. And because it was easier with all the cables and the connections and so on, we set this up into our large reverberation chamber just to have easier access with the cables. And on this side, there would be a door. You close the door with some zipper and some Velcro straps. And so it's a nice setup. You can see the dimensions here. So it's about 2 meters in height. I can nicely stand in there, and then a bit more than 2 meters of width and 2 meters 60 in length. And the height is also, remember later, the X direction. The width is the Y direction. The length is the Z direction. Then there's a steerer inside there. The steerer is also made out of metallized textile. It's about 50 centimeter in diameter and 1 meter 80 in height. And the chilling efficiency of this tent, of this metallized textile, is around 75 dB over a large frequency range. And here you can see the dimensions of our large chamber. So this nicely fits in them. And so then we have a computer that controls everything, controls the signal generator via GPIB. We have some power amplifier, and we use some logarithmic periodic dipole antenna to excite the field. We have 8 field probes. These are, unfortunately, have been our old field probes, so not the very fast ones. They are connected, as usual, by optical fibers, via some adapter box that is connected by a network cable, and then we have some optical fiber that controls the motor controller inside this chamber. And this is then how the chamber looks on the inside. Here you can see our 8 field probes. You can see the steerer, the turntable, and the quite big logarithmic periodic dipole antenna, where we use such a big antenna, we wanted to go down to small frequencies, and then obviously you need to have a rather large antenna. So as you can guess, there would not be so much space anymore inside this chamber for real equipment under test in this days. But okay, it was more about analyzing and validating the chamber. And so we measured from 200 megahertz to 2 gigahertz, with steps of about 2 to 5 megahertz, and we expected the lowest usable frequency of this chamber to be at around 500 megahertz, maybe something smaller, with a larger stirrer. We used some input power, and we get nice readings from the field probes. Unfortunately, we could not automate the stirrer, so we measured only steps of 10 degrees and did the frequencies sweep for each of the stirrer positions. And this is the result that we got for the field homogeneity. So the thick blue curve is the IEC limit. And as you can see, for most of the components and for most of the frequencies, even in this quite low frequency range, we are nicely below, except for some outliers, we are nicely below the IEC limit. Everything looks quite good. So I was really surprised, impressed how well this small chamber behaves. Okay, so we did the second measurement as required by the IEC. We loaded the chamber with 3 blocks of foam absorbers, put them on the floor, and repeated the measurement, and then it's not looking too good, unfortunately. So especially for the X component of this standard deviation, as you would expect for low frequencies, but even for very high frequencies, it's not performing that well. Okay, so this needs further analysis. So in addition to this empty unloaded chamber and the loaded chamber, I also try to do what will happen if I use some manual steering, like in the verb approach that was presented to talks before. So for, I don't know, 1.5 hours or how long the measurement took, I walked around the chamber and did manual steering with the chamber walls and the ceiling and so on. And then we also tried to have a different polarization of the antenna, because what I expected is that if we take a look into the photo, the absorbers are vertically aligned, the antenna is vertically aligned, so then there will be some huge direct coupling between the antenna and the absorbers. And as Paul mentioned in his talk, direct coupling is something that you would like to avoid in your reverberation chamber measurements or in the statistical simulations. Okay, so this is a picture of the horizontal log pair antenna, and unfortunately, I think that's no picture that I made. I should maybe have done a video while changing the walls, but you can imagine this. A person running around the tent. Okay, so standard deviation, just the basic formulas as in the IEC. You take the maximum field strength over all stirrer positions, normalized for input power, and you average this over the 8 probe locations. Do the same for this mixed quantity, and then you calculate standard deviations, and according to the standard, these standard deviations are then converted into decimals. And so this is then the result for the manual steering, and it gets better. There's a huge drop here because below 1 gigahertz and above 1 gigahertz, this has been 2 separate measurements because of the change of the power amplifier. So probably here I just did better manual steering than in this frequency range. And for the horizontal transmitting antenna, it looks much better, right? So here we avoid this direct coupling and we get much better results. And we also analyze the anisotropy coefficients. These are just also the formulas from, I think, Annex J of the IEC 261,000-4-21 standard. So you take 2 different components, normalize them to the input power, and then divide the difference by the sum, and then there's also some total anisotropy coefficient. And this is done, calculated for each stirrer, each frequency, each probe position. Then this index pair is the correlation between x and y, y and z, z and x, and this is averaged over all stirrer angles and probe positions. So these are the results. Here in this plot, everything, so ideally, these curves would be all 0, and this should be something 0.3 something. And yeah, so here is the only thing that we can see, okay, isotropy is not that good at small frequencies, and it's getting better for higher frequencies, as one would expect. So this is the empty chamber without any absorbers. This is the loaded chamber with absorbers. Here we can see, okay, it's much worse at higher frequencies. This is manual steering. Does not look too much better here. And this is the horizontal transmitting antenna. It's also not looking really good. So homogeneity improved, but isotropy did not really improve. Same can be seen if we take a look at the CDF cumulative distribution function of this anisotropy coefficients. So this is for the empty chamber. Thick blue curve is the theory, and the thin curves are the measurement. And this almost looks perfect for the empty chamber. For this loaded chamber, we can see huge deviations here and there. So for the blue and the cyan curve, which is always the one, or which are the ones that are related to the, remember, to the vertical X component with the strong direct coupling. Yeah, with manual steering, shaking the walls, it's not really, it's different, but it's not really better on average. And with the horizontal TX antenna, it's also not really that much better. Yeah, so one take-home message is, okay, you can obviously improve the homogeneity, still you can have an anisotropic field at the end. And this is also shown if we compare this total anisotropy coefficient CDF of this. So here the real outlier is before the loaded chain. Okay, so in conclusion, we tested this tank-like chamber. Empty chamber showed good performance. Loaded chamber showed bad performance. So the idea was, okay, maybe there is this strong coupling between the transmitting antenna and these absorbers. So we improved this by rotating the antenna. We could also improve it by manual steering, right? By increasing the surface area of the chamber that somehow changes boundary conditions inside this chamber. And yeah, so my take-home message for you would be, if you do immunity tests in your reverb chambers, really take care about the orientation of the transmitting or maybe also receiving antenna with respect to absorbers. If you, for some reason, to load the chamber, maybe to increase modal bandwidth. And maybe one idea would be also, instead of measuring more tuner steps, measuring more frequency steps, just measure different antenna position or measure different antenna orientation. Because this obviously gives much more flexibility, let's say, in the values. And some future work, maybe for a student at our university, would be, do we get the same results if we change the orientation of these absorbers, maybe put them on the walls? Of course, 2 gigahertz, this was the limit of the frequency that we used. We can also use horn antennas for higher frequencies, or maybe also use biconical antennas for even lower frequencies. Yeah, and so thanks for your attention. This concludes my talk, and I would be happy to answer some questions.